Welcome back. This is our third video in a playlist that contains videos that introduce trigonometric ideas, ratios, functions to students. And we're going to do several things today. One, we'll do an example that reviews some of the content of the first videos. Then we're going to press forward and learn to, among other things, I guess the goal of this video is to look at sine, cosine, tangent as not just ratios but functions. And also along the way we want to learn how to take trig values for angles that are not acute, so greater than 90 or possibly negative angles. And then finally we want to introduce the unit circle and show you ways to develop a facility with a unit circle where you don't have to constantly consult a chart or a computer or a graphing calculator. So let's begin. In this first example, we are to find a number of trigonometric values for the two acute angles in this triangle. Now, these first four deal with the angle alpha. Okay, it's located up here. This triangle has got two legs. These shorter sides are called legs, and this longest side is the hypotenuse. Relative to alpha, we would consider this to be the opposite leg, and this is the adjacent leg. To find the sine of alpha, by definition, we want to do the opposite leg divided by the hypotenuse. So that's an example of a trig ratio. It's 4/5. Whereas if I'm trying to find the cosine of alpha, I want the adjacent leg divided by the hypotenuse. That's 3/5. We're still looking at alpha, and we're going to try to find the secant. Now remember, secant is just the reciprocal of the cosine. So if cosine is adjacent over hypotenuse, secant is hypotenuse over adjacent, so that's 5/3. And if these two look like inversions of one another, they're supposed to. Finally, the cotangent of alpha that involves only legs, no hypotenuse here. And so you're going to want to divide the adjacent leg by the opposite leg for cotangent. Tangent would be opposite over adjacent. Now pay attention, we have a new symbol here. This is the Greek letter theta, and we are now down on this corner. So numerous times already in this example, I've told you that this is the opposite leg and this is the adjacent leg. And that's certainly true if you're talking about angle alpha. But from this perspective, this is now the opposite leg and this is the adjacent leg for angle theta. So sine theta is opposite leg over hypotenuse, so that's 3/5. Notice that's the same thing as cosine alpha. And tangent theta is opposite over adjacent, so that's 3/4. Notice that's the same thing as cotangent of alpha. Cosecant of theta is going to be just the reciprocal of the sine of theta. So sine is opposite over hypotenuse. Cosecant is hypotenuse over opposite, so that's 5/3. And finally, cotangent of theta should be adjacent leg over opposite leg. That's 4/3. Now, if you found that that was difficult to follow, you really need to go back to the first video in the playlist where all those basic right triangle ideas are introduced. I think you'll find it helpful. Now for some new content. What do we mean when we talk about the sine being a ratio? Well, that's what we were just doing. We were forming fractions or quotients or ratios using the sides of a right triangle. But what about when we talk about sine being a function? How's that different? Just take a lot of specific examples of sine values for lots and lots of different angles. And you'll notice that they form a whole bunch of ordered pairs. And these ordered pairs follow the rule of function where each x gets exactly one unique y. We're not here to discuss all that today. But when we talk about sine being a function, we're talking about large collections of pairs of angles and sine ratios. Here's a 70-degree angle. Here's a 0.94 sine ratio. Now, this table looks a lot different, but that's just because I've changed from angles to radians. It's the second video in the playlist where you can find an introduction to radians. Now here's a graph that includes all the ordered pairs in the second table. So on this x-axis, I'm putting those radian values for the angles. So for example, the 0.1, 0.84 is quite literally 1 to the right and 0.84 units up to the nearest hundredth. That is the sine of 1 when 1 is the radian measure of an angle. And this red graph is a sine graph. It's got a domain from negative infinity to infinity, meaning you can put all kinds of different angles into this table and expect to continuously get sine values back. The range is the y numbers that we expect to see. They go as low as -1 and as high as +1. And today you'll see how some of those negative sine values and cosine values are generated. Here's another example of a trig ratio extended to the concept of function. What I have in this table, a bunch of radian values of angle paired with the cosine values for those angles. And here's the graph. It looks a lot like the sine graph, doesn't it? There are differences, but overall, it's that undulating curve. It's got the same domain, negative infinity to infinity. It's got the same range. Y's can go as low as -1 and as high as 1, and they just repeat themselves periodically. So the big difference in these graphs is that the cosine graph begins at 0, 1, and as we proceed to the right, it decreases all the way to here, to -1. Whereas you may remember the sine graph begins at the origin and increases up to a value of 1 and then begins to decrease. A lot of similarities there and a few differences. But now, how is it that we can find values of cosine or secant or tangent or cotangent for an angle that is not acute? Okay, to develop that idea, we're going to look at a point in the first quadrant, A. It's the point 42. And we're going to draw a line segment from the origin out to that point. And between the positive x-axis and that line segment is an angle theta. We consider this the initial side. We consider this the terminal side. And this angle is wrapping around in a counterclockwise direction. I think I checked it out. It was about 25.6 degrees, but we're not worried about it. What we're going to do is find things like sine and tangent and so forth using the coordinates of that point. How are we going to do it? Well, we're going to sketch a right triangle from point A straight down to the x-axis, and then from the origin over to that intersection point. You'll notice that that forms a right triangle if you draw it carefully. You'll also notice that the dimensions of this right triangle are, in general, y for this opposite leg and x for this adjacent leg to theta. And for this particular example, the y is 2 and the x is 4. You can do tangent and cotangent right now, can't you? In fact, let's write down the formula for tangent theta right now. Tangent theta, we've always said, is opposite over adjacent, and that's still true. But see, now our opposite leg is y and our adjacent leg is x. So you could write y over x. And you could get the cotangent also just by taking the reciprocal. I think they asked us here, though, to get cosine and secant and cotangent. So yeah, we do need cotangent. Cotangent is x over y. Now, since they asked for that specifically, I can do that right now. X over y would be 4 over 2. And that, of course, just makes 2. That's the cotangent, using the coordinates of point A. Now, you won't be able to get sine or cosecant or cosine or secant. You won't be able to get any of those unless you know the what. Yes, you have to know the hypotenuse. Now, there's a formula for that. I'm going to call it r, as in the radius of this circle, an arc of which I drew here. And the way to get r is to use the Pythagorean theorem. And I'll show you the details of that up here, but there's also a great shortcut. Pythagorean theorem would say x squared plus y squared equals r squared. I mean, I know you probably saw it as a squared plus b squared equals c squared, and that's the way I learned it too. But why can't we use different symbols? We could go x squared plus y squared equals r squared. We could solve for r by just taking the square root of both sides. And if we decide that r can only be positive, then we're only concerned with the positive solution to this, and it's x squared plus y squared square root. So that's how you calculate r. And now we can do the rest of our trig values. All right? So let's go ahead and calculate that for this example. R is the square root of 4 squared plus 2 squared, which is 16 plus 4 is 20. And the square root of 20 is 2 root 5. So that's how big r is in this example. Okay, well, cosine of theta by formula would be adjacent over hypotenuse. Adjacent is x, hypotenuse is r, that's x over r. And I can figure that out now. That would be 4 over 2 root 5. And we probably shouldn't leave that radical in the denominator, so we're going to multiply top and bottom by root 5, which is going to make 2 root 5 over 5. And that's how you get the cosine. To get the secant, because that was also requested, we just want to take the reciprocal of that. So that is x over r. Or excuse me, that's r over x. Have to do the reciprocal, don't we? R over x is, in this case, 2 square root 5 over 4. I think that's pretty good. You could leave it like that, or you could reduce the 2 and the 4 to get root 5 over 2 as a better answer. Okay, and we haven't done anything with the sign. They didn't ask for it, but I suppose we ought to put down the formula for the sign here. The sign is supposed to be opposite leg over hypotenuse, and that would be y over r. And then, of course, the cosecant would be the reciprocal of that, so r over y. Okay, and there they are, and I have them summarized down below. But what I want you to notice is you can do tangent and cotangent just using the y and the x, but if you want to do any of the other four, the cosine or the sine or those reciprocals for cosine and sine, you're going to need r, and you'll have to know the formula for r. R is the square root of x squared plus y squared. Okay, and here's a summary. I don't think this table shows you anything that you did not just see. So let's move on. Here's a first example of finding trig values where we have an angle that's pretty obviously obtuse. It's not acute. In fact, looking at these coordinates, -3, 3, and drawing a right triangle like this, we know the dimensions of this right triangle right now. It's 3 tall, and it's got a negative dimension on its horizontal leg. That these are equal means that this is a isosceles right triangle, so that's 45, 45, 90. So that is a 45-degree angle right there, which makes this 45. So I have 45 here, 90 there. The total of this, if I want to measure this in degrees, is 90 plus 45. That's a 135-degree angle. And if you prefer radians like I do, the arc would measure 3 pi over 4. Okay, and it's the second video where we go through radian measure, and you can learn about that. But what we're supposed to do is find the sine of the cosecant for the angle theta. So let's just use that definition we saw a minute ago. Sine theta is supposed to be the y value divided by the radius of the circle. We don't know that radius yet, do we? And then the cosecant, of course, is going to be the reciprocal of that. So cosecant theta will be r over y. See, we have to know that r value, don't we? Well, that's easy enough. We have a formula for r. R is the square root of x squared plus y squared. And what that formula calculates is how long that hypotenuse is on that triangle. And in this case, it's square root of negative 3 squared plus 3 squared, which makes the square root of 9 plus 9 is 18. And root 18 is 3 root 2. So that's how big the radius of the circle is. It's 3 root 2. I'm going to go ahead and do sine and cosecant now. First, the hard one. Sine theta is y over r. Y is 3, and r is 3 root 2. So that's 3 over 3 root 2, which just ends up being 1 over root 2. And you can either leave it like that, or I think it's a lot nicer if you rationalize the denominator by multiplying root 2 over root 2. And you'll get root 2 over 2 for an answer. That's the sine. You know what the cosine would be? It'd kind of look the same, except instead of 3 here, you'd have a negative 3. And in the end, your cosine comes out negative. Your cosine for this 3 pi over 4 angle is negative root 2 over 2. Now what about the cosecant? I think that one's a little bit easier because you don't have to rationalize the denominator. Cosecant is r over y. That's 3 root 2 divided by 3. And cancel the 3's. And you'll get root 2. In this example, we do some similar stuff, but we get 6 new formulas because we decided to only look at points on something called a unit circle. Remember, a unit circle is a circle where the radius is known. You don't have to calculate it because it's 1 everywhere you check. Here the radius is 1, here the radius is 1, here the radius is 1. All the radii are equal to 1. And for that reason, if we go to find something like the sine of theta, we are literally doing y divided by r, but what's r? R is equal to 1, so that's y divided by 1, and that is just y. So if this is the x and this is the y, check it out. You're looking at the sine right there. The sine of theta is just the y value. It's root 3 over 2. And similarly, the cosine of theta, well, I could take you through the same development. It's x over r, but r is 1, so this is x divided by 1 is equal to x. So you're looking at the cosine right there. You don't have to divide by the radius. So for this problem, the cosine of theta is x over 1, and that's 1/2 divided by 1, and that's just 1/2. The nice thing about the unit circle is, if you have the xy pair of some point, then you have the cosine and the sine of that angle without having to really calculate anything else. So the 6 new formulas, I'm not going to develop them carefully. You can pause the video and look at them right here. Sine of theta, it's just y. Cosine of theta is just x. Tangent didn't change because tangent didn't benefit from having a radius of 1. You still have to do y over x. And then for cosecant and secant, it's just 1 over y and 1 over x respectively. And then cotangent, like the tangent, doesn't change. It's just x over y. And we'll keep this moving. Now my students are about to be assigned a challenging problem set where they're asked to do things like go onto a unit circle and find the sine of 300 degrees or the cosine of 300 degrees. And there will also be problems where the angles come in radians. So I want to go over some of those now. Of course you can look these up on a calculator, on a computer, on your smartphone, or if you get stuck, you can go on the internet and find a copy of this. They're all over the place. Just go Google, do an image search on your favorite search engine for unit circle. Okay, we may use this today if we get stuck, but I want to teach you a method that I've learned over the years. Most students find is very easy. And I've seen students try to memorize this. I've seen students just sit and study it, and that's a lot to remember. You're welcome to do it. But I contend that if you just remember that this arc right here is pi. So let's see if we can highlight this. This arc is pi. Or in degrees, it is 180 degrees. You memorize that, and you memorize these two triangles, special triangles. I think you probably learned these in geometry anyway. The so-called 30, 60, 90 triangle that has a hypotenuse of 1 will have a long leg of root 3 over 2 and a short leg of a half. The long leg comes opposite the 60 and the short leg comes opposite the 30. And then an easier one, I think, is the isosceles 45, 45, 90 right triangle. Meaning isosceles means what? These legs are the same. Yeah, they're both root 2 over 2. And we can show you how this is developed with the Pythagorean theorem at some other time. Memorize these and memorize that, and you don't have to memorize anything else. And that's what I'm about to show you right now. Okay, first of all, locating angles. We know that all the way around the circle is 360 degrees. We start from the positive x-axis and we go counterclockwise for positive angles like 300. 300 doesn't quite get you all the way around the circle. So let's start thinking in terms of 90s. Here's 90 plus 90 is 180 plus 90 is 270. We're getting close. We need to get to 300. So you have to go 30 degrees more and you'll get to about right here. It looks like about 30 degrees, or 1/3 of this 90-degree angle here. As soon as you're pretty sure that you're at the right landing spot, you should go sketch a radius, and then from the point on the circle, you should go straight up or straight down to the x-axis, and then you should complete the triangle, which in this case is a leg that appears smaller than that. All right. They're always going to ask you about triangles that have something to do with this. Now, which one do you think it is? You think that's an isosceles triangle? Do you think these are equal? Or do you think that's 30, 60, 90? Of course it's 30, 60, 90. So next question. Which leg is shorter, horizontal or vertical? Shorter, yeah. Shorter is the horizontal leg. Right there. This looks longer, it is longer, and it's root 3 over 2 in length, but now you have to remember that we're talking about the coordinates of a point down here. And that point is to the right and down. Everything down here in this fourth quadrant has coordinates that look like plus, comma, minus. So keep that in mind. When they ask you the sign, you need to know that this is negative. So we've got it. The sine of 300 degrees is negative root 3 over 2. Whereas the cosine of 300 is positive a half. Because remember, once you know these two numbers, you know the coordinates, and you don't have to divide by the radius because the radius is just 1. Let's try another example. So what do we want to do again? We want to memorize that, I guess for this example, instead of calling it pi, I'll call it 180 degrees. Right here. And of course this up at the top is 90. But halfway around the circle is 180 degrees. Okay, for this problem, we're not supposed to go that far. We're supposed to go to 150. So you pull up just 30 degrees shy of that. And if you don't know what 30 degrees looks like, it looks like this 90-degree angle right here cut up into 3 parts. So that's what 30 degrees shy would look like. So there you are at 150 degrees. Okay? Now remember what I told you? From there, just draw straight over to the origin. There's a radius. Draw straight down, in this case, to the x-axis. And then from that interception point, draw back over to the origin so you have a nice right triangle. And then ask yourself, might not be the world's best sketch, but I think you can tell which one of these is which. Is that 30, 60, 90? Or is it isosceles? To be isosceles, these would have to be equal. They don't look equal to me. In fact, I think this one's the shorter one. So this has got a dimension of 1/2, and this has got a dimension of √3/2. Yeah, those are the things you're going to have to memorize off of this triangle. You're also going to have to understand that you are right now in the second quadrant. Everything in the second quadrant has coordinates that look like this. Yes, so that's left and up means negative √3/2 and then positive 1/2. So I think we've got it. What's the sign of 150? That's the one that goes up and down. To remember that, every sign has a post, and posts go up and down. The cosine is the horizontal one, and you'll have to remember that it's a negative value over here in the second quadrant. Let's try another one. Oh, here come the radians. Okay, I'm going to go back to this. You should remember that this arc, starting at 0 on the positive x-axis and going counterclockwise over top of the circle, ends at pi. Okay, now you're going to have to understand a little bit about fractions. The number on the bottom of the fractions tells you how to cut this arc up. You're supposed to cut this arc into 4 equal parts. So cut it in half. Cut the halves in half. Those are about right. So each one of these arcs is pi over 4. Pi over 4, pi over 4, pi over... You have 1, 2, 3, 4 of them. You're supposed to have a total of 5. So to get this problem right, you have to go beyond pi by one more of these pi over 4 arcs. And that gets you to about right here. Now, go ahead and draw from 5 pi over 4. Draw from the point on the circle back to the origin. From the point on the circle, draw straight up to hit the x-axis. And then from that point, draw over. Now, it may be a little bit hard to tell, but I think it's pretty obvious that we're using a different triangle this time. I think we're using the 45, 45, 90 isosceles right triangle, aren't we? Yeah, so both of these dimensions are the same. They're both √2/2. And they're the same in a different way also. Because remember, if you're down here in the first, second, third quadrant, down here, all coordinates have both x and y negative. So that's negative to the left, and that's negative going down. We're supposed to find tangent and cotangent. Okay, what is tangent? Tangent is y over x. And in this case, you're dividing these two things that are both equal in magnitude and equal in sign. And what you're going to get out of that is a tangent of 1. How do you do the cotangent? That's very similar. Just do the reciprocal. And I'll leave that up to you. So I'm going to keep moving here. We've got 2 more pages and we're already up to 28 minutes. Let's go a little faster. Find cosine and secant for 8 pi over 3. Okay, does this occur to you that we have an improper fraction? Yeah, we really do. So what this means is, if it's an improper fraction, it means we've gone beyond pi. So what you want to do is try to figure out, well, how far beyond pi did we go? So remember, 2 pi is a trip all the way around the circle. We might even have gone farther than that. I think we did, because 2 pi is equivalent to 6 pi over 3. And we have more than that. As a matter of fact, what we have, 8 pi over 3, is we have 6 pi over 3 plus 2 pi over 3. In other words, all the way around the circle, and then 2 pi over 3 more. So we're going to go to an angle, 8 pi over 3, but it's going to be coterminal with 2 pi over 3. And I'll show you that once more. But again, the general strategy is figure out where pi is, figure out where you're going to land compared to pi, and the answer is 2 pi over 3. 8 pi over 3 is coterminal with 2 pi over 3. So what you want to do is take pi and cut it up into 3 equal parts. And if you're struggling to figure out where they are, trust me, they're right above the 0.5 and the negative 0.5 on the x-axis. And then the 2 means we have to take 2 of those. So we are quite literally at this arc right here. But one more time again, if you wanted to do 8 pi over 3, you can count it out like this. 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, 6 pi over 3, 7 pi over 3, 8 pi over 3. And there we are. Okay, enough discussion about that angle. Let's quickly jump in there and do what we're supposed to do. We're supposed to, from the point in the circle, draw down to the origin. That's your radius. It's 1 because it's a unit circle. You're also supposed to draw straight down to the x-axis. And then finally draw another line segment back over to the origin. And then if you need to, look at the chart. Which triangle do we have here? I don't think it's isosceles. I think it's got 3 different side lengths. One of them is the radius, and it's 1, but the other 2 are 1/2 and root 3 over 2, this being the larger. So I'll put those on there now. And which one of these is negative when you're in the second quadrant? Well, going left for x means negative. We mentioned everything in the second quadrant looks like this. And going up is positive. So we're supposed to find the cosine and the secant. I think we're done. Cosine 8 pi over 3 is just that leg. You don't have to divide by the hypotenuse. You just take the x-coordinate of that point. Okay, and then the secant is the reciprocal of that. The reciprocal of negative 1/2 is negative 2 over 1. I think most people would just write negative 2. Okay, we have another one of these problems where we've got this obnoxiously large angle. I don't know why anybody would go around the circle this far, but it happens. 510 degrees is a lot larger than what? 180. Yeah, it's a lot larger than that reference point there. It's also a lot larger than 360. So what you might do as a first step is to figure out that 510 degrees is 360 degrees plus 150 degrees. Check that. I think my arithmetic is correct there. What does that mean? Well, it means that if you went 360 degrees and 150 more, you'd be here, which is the same as just going 150 degrees in the first place. So there it is. There's the angle that we're looking for. It stops right here. If you're not sure where to stop, well, this time it lines up with 0.5 on the y-axis. And I think we might have actually looked at this angle once already. Not 510, but we did look, I think, at 150. And we're supposed to find sine and cosecant here. Okay. Again, that's not an isosceles triangle, is it? That has different sized legs. A longer one and a shorter one. This is a 30, 60, 90. And so that dimension, the longer dimension, is root 3 over 2, and it's negative because it's to the left. This dimension is the shorter leg of the 30, 60, 90, and it's positive. It's going up. So let's see, sine 510, that would just be the half. Whereas the cosecant of 510 would be the inverse, or the reciprocal of a half, which is 2 over 1, which is just 2. Okay. Now I've got 2 more examples, and then we'll say goodbye. On these last 2 examples, we run into a problem where these 2 triangles we've worked with today won't fit. And you know you're up against this anytime they give you an angle that is either 0 or pi or 2 pi or 3 pi. Any multiple of pi is going to either put you right here We're right here. Of course, this time we're here. We're at pi. And so what you're going to need to know about being at pi is the point on the circle, let's call it point P right here. P has coordinates that look like this. That's the x and that's the y. And so now what you're going to want to do to get all 6 trig functions is, I think I found the right table, is you're going to want to refer back to this. And you're going to get in trouble with a couple of these because they're going to have you dividing by y. That one and that one are problematic here because y is 0. So the cosecant and the cotangent are not going to exist at all. But let's go through this list and find the ones that do. So first of all, can we have sine of pi? Yes, but you just need to remember that that's equal to the y here. And that's it. That's the answer. It's 0. Can we have cosine of pi? Yes, but you need to remember that the cosine is just equal to the x, which is that. Okay, because you see, you can't fit a triangle in here at all, so you just have to go off of using these coordinates for sine and cosine values. The cosine at pi is -1, because this point is literally -1 over and 0 up or down. What else do we need to look at? How about tangent? Can we compute a tangent of pi? I think we can, because tangent, remember, is y over x, and y over x is 0 over -1, and it's okay to divide -1 into 0. You just get 0 for an answer. Now we're supposed to do the other 3. Let's see if we can come up with them. How about cosecant of pi? Well, cosecant of pi is 1 over y, if you look back on that chart, and that's going to ask you to divide by 0, and that does not exist. It's undefined. So we can't do this one. Or if you must make a report, you would write undefined. Probably shouldn't leave it blank. Somebody will think that you don't know what you're doing. What about the reciprocal of cosine? What about that secant at pi? Can you do that? Yeah, you can. Because secant is just 1 over x on the unit circle. So that's 1 over -1, and that's equal to -1. So you can do that. The other one that you can't do is cotangent. And why is that again? Because cotangent is x over y, and in this problem, the y is 0. So they're asking you to do -1 over 0, but you can't, so you have to write undefined. There are, again, any angle that looks like pi, or 2 pi, or 3 pi, or 0, or -pi, or -2 pi. Any of those pi multiples will get you in this kind of trouble, where y is 0. The other place you get into trouble, though, is at the top and the bottom of the circle. Up here at 90 degrees, or pi over 2. Down here at 3 pi over 2, or 270 degrees. And I think our last example explores that. We better hurry up because it's almost 40 minutes. Find the values of all 6 trig functions at 270 degrees if they exist. Where's 270? Well, from the positive x-axis, we wrap around in the counterclockwise direction. 90, 180, 270. 270 is down here. Okay, and the xy point down there is 0, -1. That's the x and that's the y. All right, let's go through these quickly. Sine of 270 is just the y value, and that's -1. The cosine at 270 is just the x value, and that's 0. The tangent at 270. Will we be able to write this out? I think we will, because it's x over y, and that's, oh, excuse me, I have that backwards. That's y over x, And that is a problem. That's negative 1 over 0, and that is undefined. There will be one more that's undefined. So let's go ahead and look at these. What about cosecant 270? Okay, remember, cosecant is 1 over y, and that's 1 over negative 1, and that's just negative 1. So we can do that. Secant at 270. The secant for 270 should be 1 over x, but x is 0, so that's problematic because you're trying to do this, so this is undefined. Okay, and then the last one is cotangent, and that's equal to x over y. And that one we can do because we're doing 0 divided by negative 1, and that's quite all right. That's equal to 0, so the cotangent of 270 is 0. Well, I hope that you learned something here today. Maybe you enjoyed it. My name's Eric. Have a good day.